Hello friends, my name is Derek Harder, and in this video we're going to continue looking at some of the mechanisms of neural networks. So in particular, the purpose of this video is we want to look at how a neural network is able to modify its learnable parameters of all the layers and update them so that it can correctly transform its inputs into a set of outputs. Okay, so this is basically known as gradient descent or gradient-based optimization. So as a quick review of some of the stuff we looked at in previous lectures, so each layer of a neural network performs some set of tensor transformations like we talked about. So typically dense layers do this set of transformations where it takes the input and does a matrix multiplication times some set of weights. So W is a set of trainable parameters for the layer of the network. So if you remember from previous lecture, I mean, that matrix multiplication, you can think of that as rotating the data or potentially scaling or flipping the data, that type of thing, right? It often adds that then to a set of biases. So W and B, though, often we just talk about the trainable parameters of a network, but of a layer of a network. But often it has two or three or a couple of different sets of trainable parameters. So by doing an addition, that does a translation on the data. And then, typically we need some sort of nonlinear transformation. So we'll have an activation function like the rectified linear units that are done. So the result of that becomes the output, and that's fed into the next layer, and that's done multiple times in a typical neural network. Okay? So, so the weights and biases are the trainer parameters of the layers of the network. So initially, these are all set to small random values, right? So initially, when we start training a network, these weights and biases are set to initial random variables. So initially, when these are random, the outputs for an input is just random. It's just it doesn't mean anything. Okay, so there's no reason to expect that the function will yield a correct result initially. So that's the purpose of this lecture. Is we need to add in the piece where we take those outputs and we modify the trainable parameters for all the layers of the network in order to produce correct outputs. Okay, so this training happens within a training loop for some number of epochs of training. Okay, so basically what we do to train a neural network is we're going to draw a batch of training samples and the target, the true value for each of those training samples that we want the network to predict as its output. Right? So step one, we showed that we can just slice our input tensors to get a batch of inputs to do this for this training. Then we run the model on that training input X. This is called the forward pass to obtain the predictions for that set of input. Again, this basically we talked about in the most recent previous video. So that is just applying the tensor transformations for all the layers from the input to get the output, which is our final Y predictions. And then we need to compute the loss of the model on that batch, right, using a loss function. Right. So we talked a little bit about a loss function, but we'll look at that again in this video. This needs to be some measure of the of how bad the current set of weights are doing in relation to what we want it to predict, what Y true is, what the labels are. And then we need some way of updating the weight. So that's kind of going to be the heart of this video. So based on this loss function, we need some way to use that as a signal so that if we modify the weights of all the layers, we reduce the loss. We get our outputs, the predicted outputs get closer to the true outputs that we want to get for our network. Okay, so so step 2 and 3 can be done with tensor operations. We've mostly talked about those already. So step 4 is the difficult part. So that's what we're going to be concentrating on. This video lecture is how we can take a loss function, and update the weights to improve the model. That's what gradient descent is. So it can is a way to take the loss function to calculate the derivatives of that loss function. That will give us the information that we need to change the weights in the correct direction so that the loss function will get smaller. So for gradient descent to work, it needs to be able to calculate the derivative of the loss function. So this would be a good time if you're a little bit fuzzy on what a derivative is to do a little bit of review of calculus. So I have some materials on doing some review of calculus. But real quickly and simply, so we have a function like f of x equals x squared. The derivative is the measure, the way I think of it is as the measure of the slope at any point on this smooth continuous function. Okay, so it's the instantaneous slope of the function at some point. That's one way to think of the derivative. So as you might know, that we can analytically derive the derivative. So if our function is f of x equals x squared, the derivative is going to be 2x, right? So that's what the derivative is of this function here, since this function is plotting out x squared on the plot here. So that means that, for example, at any particular point, since the derivative is 2x, that tells me that the slope when x is 2 is 4, right? And the slope should get bigger as we go this way. So like when x is 4, the slope is 8. So it's significantly bigger than it is. And when we go over this way, the slope is getting smaller. So when x is 1, the slope is only 2. And here the slope is 0, right? So whenever the slope is not changing, you'll have a slope of 0. So if you think of this as the loss function, I'm jumping ahead a little bit here, but the reason why being able to calculate the derivative is what we need for gradient descent is because if you know the slope, we know how we should change the trainable parameters of the layer to move towards lower slopes, or hopefully get down to a slope of 0, which represents the loss is 0, and we're getting perfect predictions for our for the inputs for our network. So if you understand what a derivative is, then so in this previous example, the derivative was transforming a scalar into another scalar in order to find the slope at a particular point, right? So since we know analytically what the derivative was, we could say, okay, at point 2, the slope is 4, and at point 1, the slope is 2, okay? So the term gradient is just another term for a derivative, but a gradient is usually meant to be as the concept of taking the derivative of a function that takes tensors as inputs and maybe tensors as outputs as well, right? So, and that describes our function for the layers. So our layers are a series of tensor transformations. They take tensors as inputs, and they perform tensor operations, and they give tensors as outputs, right? So we want to be able to calculate the derivatives of those tensor functions. So the loss function is going to be a tensor function. If we can calculate the gradient of it, we can use that to update the weights to reduce the loss. So in machine learning, to simplify a little bit, so again, it would be helpful if you've taken my machine learning class or a machine learning class. So if you think about a simple linear regression where you only have one transformation, like we were talking about above, a small sequence of tensor transformations. So in that case, you have an input x, and you have your weights and biases of the model. So I'm going to change my notation a little bit in the material below here because I'm using material from a slightly different source. So our textbook calls those like W and B for the weights, the trainer parameters of a model. You might often see those referred to as theta. So the theta parameters are the parameters of this sort of transformation that we're going to do. So you have the inputs, you have your trainable parameters, whether you call those W or theta. You have the target, the true label, and you have some loss function, which is meant to measure the gap between the model's current predictions and y true. So you can use your W or your theta to compute the predictions from our model, like we just talked about. And then the loss function is going to be some function that we're not going to really specify here. I'll look at a little bit more details of using the root mean squared errors here in a moment as our loss function. All right, so this is going to be some smooth function between the predictions that our model is generating and the labels that we have. So given a fixed input and given that y is true, so given that the inputs x and y true are fixed, this preceding loss function can be interpreted as a function that maps w, or theta, whichever way we want to call those, into a loss value. Okay, so the gradient descent works by, if we define this as a function, and if we can differentiate that function, we can calculate the derivatives or the gradients of some, so whatever the current values of theta are. So W0 here in our textbook means, okay, now we've got a current set of parameters of weights for a network layer or layers, and we want to calculate the derivatives with respect to our current settings for our trainable parameters. So if you can do that, if you can calculate the gradient, then you can show that if I update weight 0 to a new set of weight 1s based on those gradients. So if the gradients tell me which direction I want to go. So if I just go in the opposite direction of the gradient, so again, here the gradient is positive. So it was 4. So that means that I want to go negative. I want to change my weights so that we will go in the opposite direction, a negative value, in order to go towards a smaller gradient. And that's all that this equation is saying here. So we're going to have to, we'll multiply the gradient of our loss function times a learning rate. Talk more about that in a moment. And then we subtract that from W0. That'll have us go in the opposite direction to get our new set of updated weights, W1. Okay? So that's the basics of what we're going to do for each of the learning steps if we have a loss function that we can calculate the gradients for. Okay, I decided to cut this video into a couple of pieces for the section 2.4 on the engine of neural networks. I'm trying to keep these videos into short chunks, like 10 and 20 minutes each. So far in this piece, this is a good point to stop and think about. Just to review a bit, so we basically looked at, we started by trying to give an overview of what batch gradient descent is, and we're going to go into some of the details of gradient descent in the next part. But then we looked a little bit of a review at derivatives, and we talked about the gradient. So the gradient is just the derivative of a tensor function. Okay, so the things that we work with, the loss functions that we use to measure how well the network is doing, are going to be differentiable. And since these are, the loss functions are going to be functions of tensors, these are called gradients. So the gradient gives us all the information that we need in order to modify the weight so that we can follow the gradient towards lower loss on our loss function. Okay, so that's kind of the main, most important things you should understand from the part so far. Okay, so I hope it was useful for you, and let's stick around and come to the next one if you want to look at a little bit more of the details of gradient descent.